Good morning, champ. Bernoulli isn't just theory, it's the heartbeat of every real fluid flow. Tanks draining, nozzles spraying, flow meters measuring, and jets hitting targets. In this episode, we'll see Bernoulli in action through three powerful examples: a draining tank, a Venturi meter, and a free jet striking a wall. By the end, you'll know how to turn Bernoulli's energy balance into real engineering predictions. Let's start with the foundation. For steady, incompressible, and frictionless flow along a streamline, the sum of the static pressure, the dynamic pressure, and the hydrostatic term stays constant. In symbols, pressure plus 1/2 times density times velocity squared plus density times g times height equals a constant. This is Bernoulli's equation in pressure form. It tells us that pressure energy, kinetic energy, and potential energy per unit volume all trade off. If one rises, another must fall. Now let's use it. Imagine a tall water tank standing quietly, open to the atmosphere, with a small circular opening near the bottom. When we open the hole, water shoots out as a jet. How fast does it leave? We apply Bernoulli's equation between 2 points, point 1 at the free surface of the water and point 2 at the opening. At the surface, the pressure equals atmospheric, the velocity is nearly zero, and the height is h above the hole. At the opening, the pressure is also atmospheric, the velocity is unknown, and the height is zero. Plug those into Bernoulli's equation, cancel the equal pressures, and neglect the small velocity at the surface. That gives 1/2 times density times velocity squared equals density times g times h. Simplify it, and you get velocity equals the square root of 2gh. That's Torricelli's theorem. The velocity of the jet is the same as the speed an object would gain if it fell freely from height h. The potential energy of the water column turns into kinetic energy of motion. If the opening area is A, the flow rate is area times velocity, or A times the square root of 2gh. In practice, viscosity and jet contraction reduce the flow a bit, so we multiply by a discharge coefficient, usually around 0.6. That gives Q equals CD times A times the square root of 2gh. Now let's measure flow. The Venturi meter. Imagine a smooth pipe that narrows in the middle and then widens again. The wide section has area A1 and the throat has area A2. We measure the pressure at both sections with 2 small taps connected to a U-tube manometer. The height difference of the liquid column tells us the pressure drop between the 2 points. Continuity says area 1 times V1 equals area 2 times V2. For a horizontal pipe, Bernoulli gives pressure 1 plus 1/2 density V1 squared equals pressure 2 plus 1/2 density V2 squared. Combine those two relations, eliminate V1, and solve for V2. The result is V2 equals the square root of 2 times the pressure difference divided by density times 1 minus the ratio of A2 over A1 squared. The flow rate is area 2 times that velocity. This is how a Venturi flow meter works. The fluid speeds up through the narrow throat, pressure drops, and that difference tells us the flow rate. If the throat is too narrow, the pressure can drop below the vapor pressure, causing cavitation. Small vapor bubbles that collapse violently. That's why Venturi shapes are smooth and gradual, to recover pressure gently. Finally, let's make Bernoulli deliver force. Picture that same jet from the tank striking a flat plate head-on. The jet leaves the nozzle with velocity v equal to the square root of 2gh, cross-sectional area A, and density. Newton's second law says that the rate of momentum change equals the force. So the impact force is density times area times velocity squared. If the plate is tilted at an angle theta, only the normal component of velocity changes. The force becomes density times area times velocity squared times cosine of theta. When the plate is vertical, cosine theta equals 1, and the entire jet momentum acts on the plate. That's how hydraulic jets can clean surfaces, cut materials, or drive turbine blades. Bernoulli gives the speed, Newton gives the push. To recap, Torricelli's law shows how potential energy becomes velocity. The Venturi meter converts pressure differences into flow measurement, and the jet impact transforms velocity back into mechanical force. So, champ, Bernoulli isn't just elegant mathematics, it's energy at work. From calm tanks to roaring jets, it's the same equation telling us how fluids trade pressure, motion, and height in perfect balance. Keep that math flowing and your curiosity flying.